Okay, let's start. So we'll discuss domain model. So domain model is a class diagram. So it describes the database. It has a direct translation into the database schema. So now our job is to extract this domain model class diagram from this natural language description. So here's the ASU course registration problem statement. At the beginning of the semester, students may request a course catalog, etc. So it's just it's slightly different from the your course project. But it's in most part it's the same. So how to identify possible classes? You look for nouns. So for this sentence, you see a noun, semester. So students, course catalog, course offerings, and semester again. So you saw it before. So now we have 4 nouns. So possible classes include these 4. So now let's leave it like that. We'll later eliminate some of the potential classes. So now we're just looking for nouns and gathering any possible classes. So information about each course, that's a noun. Instructor, department, prerequisites, students. We saw students before, so we don't have to add it again. Informed decisions. So now we see these possible classes. Course, we see the noun is information about each course. So now this can be easily modeled with a course plus a bunch of attributes. And then we see the others. You may see the informed decision as a strange class. So we'll see that we'll eliminate that class later. The new system will allow students to select 4 course offerings for the coming semester. So the only new noun is system. All the others are seen before. And each student will indicate 2 alternative choices in case a course offering becomes filled or is cancelled. So the new noun here is alternative choice. No course offering will have more than 40 students or fewer than 10 students. So no new classes, all have been seen before. A course offering with fewer than 10 students will be cancelled, no new classes. So we go faster. So now we see 3 new possible classes: registration process, information to the billing system, and professors. Now we see a new noun, professor. And now there's a period of time that students can change their schedule. So we see 2 new nouns, period of time and schedule. Students must be able to access the system during this time to add or drop courses. So no new classes. So now we have found all these potential possible classes. We move on to possible associations. So associations are verbs. So you look for verbs at the beginning of each semester. Request, that's a verb. A course catalog, containing, that's a verb. Needed for the semester. So students requests course catalog. Remember, you put it into a singular form, active voice. So a course catalog contains course offering, and semester needs a course offering. So when you see contains, it's an obvious candidate for a composition or aggregation relationship. So information about each course, such as instructor, department, and prerequisites, are included to help students make informed decisions. So course catalog includes course information. Course catalog helps student makes informed decision. So the new system will allow students to select 4 course offerings. So system allows student selects course offering. So we'll go faster now. Now we identify more actions. A verb. Students indicate alternative choice. In case the course offering becomes filled or it's cancelled, so it becomes filled. If you put it into an active voice, it's actually not specified who fills the course offering. So we'll put a question mark there, and it's not clear who cancels it. So no course offering will have more than 40 students or fewer than 10 students. So course offering has student. So a course offering with fewer than 10 students should be cancelled. So we saw the cancel verb before, so we don't add any new association here. So registration process is completed for a student. A student completes registration process in active voice. System sends information to billing system. Billing system bills the student. So the statement says students can be billed for the semester. So it doesn't say who bills the student. So we infer from domain knowledge, from common sense, that it is the billing system. Professors must be able to access the online system to indicate which courses they will be teaching and to see which students signed up for their course offerings. So professor accesses system, professor indicates course, professor teaches course, professor sees a student. Student signs up for course offering. So, and then student changes schedule. Student accesses the system. Student adds course. Student drops course. So now we identified all these possible associations. So now we need to decide which ones should not be in the class diagram. So are there any classes irrelevant to the problem domain? So are there any classes vague and ill-defined? So let's look at some of these. So the ones marked OK should be legal, should be classes in the class diagram. So that's student, course offering, course, department, and professor. Now, are there any classes irrelevant? Course catalog. This is irrelevant because this is something that you print out, or you pull from a user interface, or you print out. So it's a physical thing that's not really stored in the database, right? Remember, we're trying to design the database, persistent data. So course catalog is generated on the fly from all the information contained in the database, but it itself should not belong in the database. So it's a physical system generated entity. That is, you generate it and print it out. So in structure, we remove that. That's redundant because we already have professor. We can choose to name this class instructor or professor, but we should make the terminology consistent. And here we pick professor. So what others are irrelevant. Informed decision. Student makes an informed decision to decide on some courses to take. So this is a mental process of a student. Therefore, it doesn't belong in the database. Billing system is an external system. So we're now trying to develop the registration system. So billing system is outside of the scope. So are there any classes that are vague and so information? So information is used in a number of places. Send information to the billing system. Exactly what information? So it needs to be specified more clearly, possibly as attributes on other classes. For example, here information here should be attributes on the course class. It shouldn't be a separate class. Are there any nouns that should be attributes of classes instead of classes themselves? So semester, should we put it as a separate class or an attribute? It's a design decision. So here we decide that it should be an attribute of the course offering class. But it may be necessary to put it into a separate class by itself if it needs its own attributes. But in here, it doesn't have any attribute itself. It's a very simple class if you put it into a separate class. So we decide to put it as an attribute of course offering. So prerequisite, should it be a separate class? Well, it's actually a role that the course class plays in a association. So it's not a separate class. System. So the professor accesses the system. The students uses the system to sign up to add courses. So the system is the thing we're trying to develop. So it's the implementation construct. So it's not something that should be stored in a database. So it should not be a class. Alternative choice. So there's one line that says students indicates alternative choice for a course in case it becomes filled or canceled. So it's the same as a course offering. So some course offerings are your primary choices and some are alternative choices. So we don't have to put alternative choice as a separate class. Registration process. So that is the process of registration when you log into the system, select some courses, and delete some courses, add some courses. So that is the active operation which has an effect on the database, but itself should not be modeled in the database. Right? It's a transient. If you do it, you add a course, that's an operation that should be modeled in the use case diagram. Of course, it has an effect of adding a course in the database, but itself is a transient operation. So, professor is okay. Period of time is vague. So there's a period of time where you can add and drop courses. So it shouldn't be a separate class. Rather, it should be modeled as OCR or as attributes in the classes. And schedule, students select a schedule. What is a schedule? It's just a collection of course offerings and their time slots, right? So it shouldn't be a separate class. So so now we have identified the right classes by eliminating classes based on these criteria. Any class is irrelevant. That's course catalog, which is a physical entity generated by the system, not the database. Shouldn't belong in the database. And billing system, which is an external system. Are there any classes vague and ill-defined? That's informed decision, information, and period of time. Are there any classes redundant? Instructor and professor, you should choose one. That's redundant. Alternative choice is the same as course offering. Should be if you keep course offering, you should not have alternative choice. Should any classes freely be attributes? So semester, we decided to model it as an attribute, but if you do need to add more attributes to the semester class itself, then perhaps you need to model it as a class. It's a design decision depending on how much detail you want to describe the semester. Do any classes names describe a role? That's prerequisite. Prerequisite is a role that a course plays, not a class itself. Do any classes describe an operation? Registration process is an operation, so that should be put into the use case diagram, which we'll discuss later. Do any classes describe implementation constructs? That is the system. That is the system we're trying to develop, trying to design, implement. So now we need to look at the possible associations and see which ones we should eliminate. So we look at, are there any associations between eliminated classes? Then these associations are automatically eliminated. Any association is irrelevant to the domain model. Again, you see if it belongs in the database or not. Do any associations describe an operation? Can ternary associations be decomposed into binary ones? So you always use ternary associations very carefully. Most ternary associations can be described into into multiple binary associations. If so, you should try to use binary associations. Are there any associations, derived associations? So here you see three classes connected by three associations, X, Y, Z. So in some applications, perhaps association X can be inferred from association Y and Z. If so, then we just delete this X association and only leave Y and Z. So try to remove redundancies. Sometimes you cannot. Sometimes you do need three associations. But most of the time you can infer one from the other two. Do any associations describe implementation constructs? So again, we do not describe implementation constructs in this requirement stage. We only describe the conceptual constructs. So we look at the associations. First, we look for the classes that have been eliminated. That is, course offering, all these, system, course catalog, registration process, billing system. So all these have eliminated classes, so the associations are automatically eliminated. Now, student selects course offering. That is an operation that you perform while you're using the system. So perhaps it should be put into a use case, but it's actually it's actually a fine-grained operation that should be put into the add course use case. But we'll discuss use cases later. But in any way, it is a transient operation. So students indicate alternative choice. Someone fills course offering, someone cancels course offering. So all of these are operations. We don't even care who actually fills course offering and cancels course offering. But we know that someone does it, it may have an effect on the database. So that is, if you cancel a course offering, perhaps you should delete the course offering object from the database. But this cancels itself is not describing a persistent relationship between objects in the database. So you should try to make a distinction here. If a professor teaches a course, then that is a persistent relationship between the professor class and course class that should be kept in the database. But if a professor selects a course or indicates a course here, it's not a persistent relationship, right? He indicates a course and perhaps does something selected, and then he pushes a button, and then association is established between professor and course with let's say professor teaches a course. So therefore indicates or selects a course is a transient operation, while teaches is a persistent relationship. So you should try to distinguish between these two. So professor sees student signs up for course offering. All these are operations: add, drop. So now we have come up with the initial class diagram design. So we have identified 5 classes: student, professor, department, course, and course offering. 2 associations: course offering has student, so, and professor teaches course. So 2 associations between these classes. Now we refine it a little bit by adding more associations, which is inferred from domain knowledge. In other words, common sense. That is, the problem statement often does not contain every detail of the domain. So sometimes you need to infer information based on domain knowledge. So department appoints professor. So that is the inferred association. Department offers course, and prerequisite So a course is a prerequisite for another course. So this is an association from course to itself, essentially with a role name prerequisite. So this is not immediately apparent from the problem statement. Problem statement says students must satisfy some prerequisites before he can take a course. But as a student, you should know that a prerequisite should be a self-association. This is inferred association. And then course contains course offering. Again, this is not explicit in the problem statement. So this is another inferred association. So, any questions so far? So you see the difference of this domain model from your course project. Difference is perhaps only one is here, where we don't model the department. We model the university as offering a collection of courses. All the others are perhaps the same. So now we have the domain model. We identify attributes next. So attributes usually correspond to nouns followed by possessive phrases. So possessive phrase is a student's address. So this students, that's a possessive phrase, or password of student. This of indicates a possessive phrase, that is student possesses a password, possesses an address. So so now you can infer that password and address should be attributes of the student class. Adjectives representing a specific enumerated values. So fall semester, fall is an adjective modifying the semester noun. So this should indicate a enumeration value. That is, a semester could be either spring or fall. PhD degree. So PhD should perhaps be a attribute with possible enumerated values of master's, bachelor's, and PhD. So only specify attributes that directly relate to the application domain. That is, most attributes will not be given in a problem statement, and will have to be obtained from domain experts or application documentation or domain knowledge. So that's the case for your course project. Many of the attributes will have to be designed by yourself. So now these attributes are student has. We saw password, right? We saw address. Now you can infer perhaps you need a date of birth, date of admission, level of study, that is the first, second, third year, a mode of study, full-time, part-time, quad-time, year of study, and other names, perhaps the English name in addition to Chinese name, a surname, user group, user ID. So this is the ID you choose to log into the system. So all the others are similar. So are there any attributes closely related to the class they are in? So an attribute that seems irrelevant to the class may indicate that it should be put into a separate class instead of being put into an attribute of a class. So a class should be coherent, that it should describe one thing, should have one purpose. So should any attributes really be classes? That is, can the attribute exist independent of the class itself? So this really often depends on the application. For example, address. So it's an attribute of the student class. But sometimes you may need to pull it out into a separate class if it's important enough. That is, if the address itself contains many attributes, then you pull it out. So it really depends on the application. So should any attributes be in an association class? So if an attribute depends on the existence of an association, it cannot exist independent of an association, then perhaps you should pull it out and pull it into association class instead of being put into one of the classes connected by the association. So have object identifiers be included as attributes. So every object has an internal object identifier. They should not be attributes. So, but some IDs are attributes, like the user ID of students and user ID of professor. These are visible to the user because they need to use it to log into the system. What should be eliminated are the internal object IDs stored in the database. They are not part of the attributes. So next we come to operations. So we add operations, some operations now, but most operations will be added later during analysis and design. The most common ones are obviously get and set, right? When you have an attribute, you should get it and set it. So for each, obviously, only the public attributes should have get and set operations, and typically we do not show get and set in the class diagram. For each association, we need to identify name, optional name, row names, multiplicity, and association class if necessary. So place all the domain model terms and their definitions in a glossary of terms data dictionary. It acts as a dictionary of terminology terms used throughout the development process during analysis, design, implementation, testing, and maintenance. They should be kept consistent throughout the process. So here's the associations added with the additional annotations. So we see department appoints professor. The multiplicity is 1 at the department end and 1 star at the professor end. Essentially, it says a professor should work for exactly 1 department, and a department should appoint 1 or more professors. So department offers 1 or more courses, and each course should be offered by 1 and only 1 department. So this rules out any joint course offerings, say between the CSE and ECE department. So in here we only allow course offered by exactly 1 department. So a course is a prerequisite for another course. So we have star here. Remember, star is a shorthand for 0 star. It says a course may have 0 prerequisites or more prerequisites, and each course may be a prerequisite for 0 or more courses, other courses. So a course contains one or more course offerings. So a Comp211 has a course offering in the fall and another in the spring. So obviously, a course should have at least one course offering, but can have more. Professor teaches course offering. So notice here, professor teaches course offering, not course. So a professor always teaches a specific course offering in a specific semester. So each course may be taught by multiple professors at different course offerings. Even for the same course offering, you may have multiple professors. So in the spring, the Comp211 course offering is taught by 2 professors. In the fall, it's taught by 1 professor. So students enrolls in course offering. A student can take 0 up to 4 course offerings. So a course offering should have 0 up to 40 students. So we'll see later that it's actually not very accurate, because this multiplicity is valid during the add drop period. But after the add drop period, the course offering should have a minimum number of students. But this class diagram is used both before and during and after the add drop period. Therefore, you should make the multiplicities more general to fit both the transient period where students can add and drop courses. Therefore, a course offering's number of students can drop below 10, and the steady state where the course offerings number of students is fixed. Enrolls in is association class. Is indicated by this dotted line connecting it to the association between student and course offering. It describes the association. Now, why do we need this association class? Why not adding an association class for all the other associations? We add it because we need to put an attribute grade in the enrolls in association class. So we discussed this before. If you want to describe a grade, if you pull it into the student class or pull it into the course offering class, they're both very awkward. So because it's not really an attribute of the student or the course offering, it's really for each pair of student course offerings. So it really belongs to the association class. If you didn't have this grade attribute, then it's not necessary to have the enrolls in association class. So for example, teaches is the association between professor and course offering. It doesn't have a association class associated for it. It's just a association name. So the difference is that you don't need any attributes in the teaches class if you pull it into a separate class. So it's redundant. It's not needed. Only if you need to specify some attributes, then you design a separate association class for a given association. Similarly, offers doesn't need an association class. So any questions on this class diagram? So adding attributes, you should try to have meaningful names. If you have item price, write item price. Don't write ITPR. short description, perhaps as annotation. Payment is a transaction to record a remittance. Deposit is the initial amount paid by the company on a purchase order. So you should add a description to make it easy to read. UML allows you to add notes to a class diagram, which can contain arbitrary text. Aliases. So that is, if you have customer, client, they are synonyms. Therefore, you should try to choose one. Similarly for instructor, professor, but that's a class name. Here for attributes names, it's the same. You should pick one among a group of synonyms. Acronyms, shortened names. So you can use either request num or REQNR to represent requisition number. So among the three, you should pick one and use it consistently. Length, so as found in the real world, that is the number of digits or letters. Allowable values can be either continuous or discrete. So a price is a range of values from 0 to 10,000. It can be fractional, therefore it's a continuous value. So you note the range 0 to 10,000. Typical values, that's optional. And exception handling, that is, in case the price rises above 10,000, what happens? You should add a note to indicate how to handle the exception. So discrete attributes like marital status is you're either single, married, widowed, or divorced. That is the enumerated value with 4 possible choices. So you note values and meaning of each. So encoding, that is the physical representation of the value. So only if no choice is allowed in the design, that is, you specify the choice early, then you put it into the requirements document. Otherwise, you postpone it. You don't specify the encoding until later. Supplementary, that's other information, any other information that may be helpful, you put it into a note to the attribute. So now we can add generalization to it to simplify the class diagram. So classify classes according to similarity of attributes and operations. Then extract them and place them into a more general class, a superclass. So look for kind of statements that are true in the real world. So a sedan is a kind of car. A car is a kind of vehicle. That indicates a generalization relationship. Do not nest too deeply. 2 to 3 levels of generalization is okay, but 4 to 6 maybe, but more than 10 levels is too deep. You shouldn't have too deep class hierarchy. So the goal is, that should wake you up. The goal is to have a simplicity of representation and clarity. So here's the example. Professor and student, you design a superclass for it by pulling out the common attributes like name, date of birth, address, etc. Pull them into a separate superclass person, and let professor and student both be subclasses of person. Now you have suppose you have this district class which is not present in the problem statement. We just add it for illustrating how to handle associations after you do the generalization. So suppose professor lives in the district Kowloon or Xinjie. So student also lives in the district. Now, if you pull out the person as a superclass, you can actually pull out the association to be between district and person, because it's the same association, right? Professor lives in district, student lives in the district. So it's actually more clear and more succinct to have a single association between person and district rather than two associations between professor and student. It's not wrong to have two associations, but it's more clear to have one association here. Now, sometimes it's necessary to adjust the multiplicity of an association. So now suppose you have PG student and UG student, both subclasses of the student superclass. They both can enroll in courses. But a PG student can take 0 to 3 courses. A UG student can take 1 to 5 courses. Now, if you pull out the association to be between course and student, what is the multiplicity here? So the multiplicity should be the union of the previous two multiplicities, 0.5. So the minimum is 0 because PG students can take 0 to 3. The maximum is 5 because UG students can take 1 to 5 courses. So as you can see, if you do this, you lose information, right? In the previous class diagram, you know that a PG student can take 0 to 3 courses. But in the new class diagram, you only know that a student can take 0 to 5 courses. You've lost information. So that's the price you pay for a simpler class diagram. But you can use OCR to define more specific constraints to add back the lost information. Generalization. So now we have going back to the example. We have 5 classes with their attributes. Now we look for common properties and semantics among the classes and put them out into superclasses. So we see all these are common attributes: user ID, password, user group, surname, other names, address, date of birth. So we can pull them out into a person superclass and have student and professor inherit from the person superclass. And then course offering has association to both student and professor. Then how about let's pull out these two associations, pull them into a single association between person and course offering. So it actually turns out that is a bad idea. You should not do that, because these two associations are different. Student takes a course offer, enrolls in the course offering, while a professor teaches a course offering. So you should not pull it out into a single association, because these are very different. Only if the two associations are the same associations, they have the same meaning, then you can pull it out into a common association. So here you should keep the two associations here. Generalization. So here, as I said, if you have a single association, then it's incorrect. So this one is correct because these two associations have different meanings. So after working on all the other classes, we come up with this class diagram. We have a person as a superclass. This inheritance, this generalization relationship is disjoint and incomplete. It's disjoint because a person cannot be a student and a professor at the same time. It's incomplete because there are other persons besides students and professors. There are secretaries and other people. So all the others are still the same. So, constraints. Is the multiplicity of the course offering and of the enrolled in association realistic? If you look at, I think I'll turn off the noise. So, look at this so look at this particular multiplicity. A student enrolls in 0 to 4 course offerings. It's really 0 to 4 course offerings in one semester, right? A student can take a lot of course offerings during his stay at a given university during the 4 or 3 years. So 0 to 4 is not really realistic. So really you should put 0 dot dot star, right? But if you do that, then you lose information. So you want to have 0 dot dot star here, while at the same time you want to specify that a student can take at most 4 courses in one given semester. Then OCR can help you. So this previous class diagram says a student can enroll in at most 4 course offerings during their entire time at the university, which is unrealistic. The real constraint is student can enroll in at most 4 course offerings in one semester. So it's unknown the total number of course offerings in which a student will enroll. The max card should be star. So to document the fact that enrollment in a semester should not be more than 4 course offerings, we use OCR. So here's this OCR statement. It says student dot course offering. So there's actually a context above it which is omitted. The context is student. So you do a navigation student dot course offering. That is all the course offering objects associated with the given student object. You say union for all. Suppose C1 and C2 are the 2 course offerings, and they satisfy the following conditions. C1 offering ID is different from C2's offering ID. That is, these are 2 different course offerings, and the semesters are the same, and years are the same. Then the size of this set should be less than or equal to 4. So we won't ask you to design a complicated OCR statements in the exams. So this is just for information only, to show what OCR can do. So OCR, this statement essentially says, if you look at a student and grab all the course offering objects associated with him, among all the course offering objects, perhaps 30, then you pick out any 2. And if these 2 are different course offerings, but they are in the same semester and same year, then you put them into a set. And then you compare the size of the set to 4, and enforce that the size is less than or equal to 4. So essentially, it says that a student's course offerings in any given semester and at the same semester and same year, but different course offerings, they must be no more than 4. So here we have 20 minutes left. Now I'd like to give you a exercise to work on. If you have printed out the notes, don't look at it, because the point of the exercise is to have you do this yourself and then compare to the standard answer. So you should draw a class diagram based on the problem statement. This won't be graded, don't worry. I just want to get back some feedback and see what mistakes you're making.